Afternoon. People are joining from all over the place. Great to see how many people have registered for this. This is our annual, the start of our annual workshop for the Go Green collaboration, obviously being done in a different format this year. And this is coinciding with the data release of all the data taken for the program, as it's 1 year after the end of the survey. And so that's why we've invited all of you to join and help us celebrate the end of the survey, have a look at some of the first results, and introduce you to how you can get your hands on the data. So just a quick overview of what's happening today. So I'm going to give you a brief summary of the Go Green survey now, followed by Adam, who's going to talk about the G-class survey, which is a similarly motivated survey at slightly lower redshift that's also being released with the Go Green data. We'll then have a series of science talks, starting with those that have been published and then moving on to some works in progress. And towards the end of this afternoon, I'll come back to talk to you about the actual data release, where you can find the data and how to use it. This talk is being recorded, okay, and will ultimately be posted publicly next to the agenda, so be aware of that, please. We have a very tight agenda, so I think what we'd like to do is, if you have questions, please put them in the Zoom chat. The speaker might just address them directly in the chat window, but also when we have the discussion sections here in the agenda, we can come back to them. And I'll be monitoring the chat to pick out questions. So Go Green has been a very large collaboration, a very active collaboration. Many people have contributed to the data and the results that we'll be talking about today. The people most active in the data production and reduction and analysis are those in the big green box at the top. It includes a number of postdocs and students highlighted in yellow, and people from all over the world have contributed to this work. Other Go Green members in the green box below that are also a key part of the collaboration. And we've had help during the preparation of the data from a number of people with observing or data reduction who are not Go Green members formally, but have also contributed. So I would like to acknowledge all of them. So I want to very briefly start with the scientific motivation for Go Green, which is also largely the motivation for G-class. These are studies of galaxy clusters. And clusters, there's lots of reasons why one would want to study these systems. As very rich environments with many galaxies at the same distance, it allows for a relatively easy relative comparison of galaxies where they're all in one place, and you can relatively efficiently study that galaxy evolution. The other advantage is that nearly all the baryons are observable because the hot gas, which is the dominant baryon component, is heated to X-ray temperatures. That's what you see as the purple glow in this nice picture of Abell 1689 on the right. And so unlike with galaxies, individual galaxies, here we can see almost all the baryons. As very massive rare systems, they're cosmologically sensitive. That is, the number, the abundance of clusters, and their structure is sensitive to the background cosmology. And that actually motivates a lot of cluster studies that have been done over the past decades. They're also extreme environments, so high density environments. And so you see rare and extreme processes that are interesting to study. And also important is that actually the mass and baryon accretion history of the clusters as a whole is pretty well understood from theory. Once you have a cosmological model, we understand the rate at which these things have grown. And that actually allows you to make some interesting toy models to connect that accretion to what we observe. So Go Green and G-class, look at all those things, but I'd say are primarily designed to provide insights into galaxy evolution. In particular, an important feature of the evolution of the galaxy population has been the decline in star formation rate over the past 10 billion years or so globally, as galaxies have transformed from highly efficient starburst type systems at high redshift into the sort of quietly star-forming galaxies, nice regular disks that we see today. We don't fully understand the cause for this decline. It's obviously related somehow to the baryon cycle, where gas flows into dark matter halos, cools to form galaxies. Gas can be ejected through supernova and AGN feedback and recycle back into the halo in the galaxy. And some disruption or slowing down of this cycle ultimately leads to the slowing down of galaxy formation. And at least one component of this is something we call quenching. That is, if we look at the stellar mass function of galaxies, this is from, it's been shown in a number of surveys, but these Schechter functions are taken from Adams' work on UltraVista. If we look at the star-forming galaxy population, the stellar mass functions don't evolve strongly with redshift. And that's actually a surprise, because if galaxies are forming stars, they should be growing and therefore getting larger and moving to the right. At the same time, what's happening if we look at the population of galaxies that are not forming any stars, that we call dead, okay, their abundance is growing rapidly with time, rapidly and significantly with time. And so what's clearly happening here is that galaxies that are normally just forming stars like everything else shut off and become completely quiescent. Whether that happens slowly or quickly, we don't fully know, but there is this transformation from star forming to not star forming. Much of this is almost certainly related to various feedback processes, again, supernova and AGN. And these are processes that are strongly mass dependent, and they lead to a quenching efficiency that is strongly dependent on the stellar mass of the galaxy. But interestingly, when we look at galaxies in clusters, we find that they are also more likely to be quenched, even at a fixed stellar mass. That's shown in this stylized plot here on the right, where we'll just look at this fraction of dead galaxies, let's call them, as a function of their stellar mass. And if we compare isolated galaxies to galaxies in clusters, the fraction of dead galaxies is enhanced in clusters. And at least one of the pieces of this baryon cycle that's likely to be disrupted in clusters is the inflow of gas from cosmological sources. That gas is no longer accreted onto individual galaxies, but is dominated by the global potential. Whether or not other things are disrupted, depends a little bit on the details and where you are looking in the cluster. But at least for much of the cluster population, it's reasonable to take the hypothesis that all these other processes, star formation, the conversion of molecular clouds into stars, the feedback associated with that, the rate of gas outflowing from galaxies, doesn't care that the galaxy is in a giant cluster or not. And so that actually allows you to make a relative comparison between cluster galaxies and field galaxies, where a lot of the complex things we don't understand are the same in both environments. And again, because we have this good understanding from theory of what the gas inflow rates, the baryon accretion rates are as a function of time for galaxy clusters, we have some hope of understanding and unpacking some of this complex physics by comparing galaxies with and without this cosmological accretion. And what's particularly interesting is that theoretical models of all types and varieties have had great difficulty reproducing these observations. And their failure is generally in the sense that they overpredict how much excess quenching there should be in clusters. So these lines here, adapted from Hirschman et al., showing one particular theoretical model, but this is generic of almost all of them, that they're tuned to get the quenched fraction correct for field galaxies, but they tend to overpredict the fraction for cluster galaxies. We have lots of ideas, and we know that things happen, extreme things happen to galaxies in extreme environments, but including these things or changing the way they work only makes this problem worse. There's something here that we don't understand related to something more fundamental about how satellite galaxies evolve. We can use redshift evolution as an important discriminator here because the infolding galaxy population evolved so strongly with redshift. Star formation rates are orders of magnitude higher at high redshift. The gas contents are much higher at high redshifts. Dynamical times are much shorter. So by comparing things at high redshift to low redshift, we get another angle on trying to figure out what's happening. So with that scientific motivation, I'm now going to talk about the basic overview of Go Green and G-class a little bit, but mostly Go Green. There have been a lot of spectroscopic cluster surveys over the past couple of decades, many of them motivated by cosmology, but not entirely. And most of them restricted to redshifts less than about 1. G-class pushed to redshift 1.3, and Go Green was largely motivated by pushing to as high redshift as we can, about redshift 1.5. Here's a good way to have a look at the sample and how it compares with what else is out there. Here I'm plotting the cluster mass as a function of look-back time, or redshift, on the x-axis. And so the Go Green systems are these green circles at reasonably high redshift, look-back times approaching 10 billion years. They also span a wide range in halo mass. That's, again, by design. We want to decouple the role of galaxy stellar mass from halo mass in galaxy evolution. So we have a wide range in halo mass. G-class are the red circles here. There are also 5 G-class clusters that are part of Go Green, so there's an overlapping sample there. And the red triangles are from GEEK2. That's also a Gemini spectroscopic program for groups, low mass systems at the same redshift. What I have on here are tracks showing the expected growth in mass for different systems over time. And so we see that we span a range from things that will ultimately end up being much less than the mass of the Virgo cluster to things that are much more massive than that of the Coma cluster. So a wide range. The surveys are also designed to probe a wide range in stellar mass. And here I'm showing the stellar mass of all galaxies spectroscopically confirmed in the G-class and Go Green samples, a function of redshift. The red points are quiescent galaxies, so those that are not forming stars. And that sample is complete almost down to 10 to the 10 stellar masses over the whole redshift range. The green triangles at the top here indicate the location of the clusters in the sample. So Go Green was built on a Gemini large and long program in the first round of such programs, started in 2014. It was originally a 3-year, 438-hour program, primarily to obtain spectroscopy of 21 galaxy groups and clusters. Ultimately, this was extended to 530 hours over 10 semesters, and it used both Gemini telescopes. The program was very well supported by Gemini, by the directors, by the staff, and by the community to allow us to get almost 100% of the original allocation executed. Go Green took advantage of new red-sensitive detectors, which allowed us to push to the highest redshifts we could from the ground. And that was the motivation for building on the G-class strategy. Here's the list of all the clusters that are in Go Green and G-class. The last data for Go Green were taken last July, and as promised, a year later, we are releasing the data. Here's just a picture of one mask of multi-object spectroscopy taken in nod and shuffle mode to get excellent sky subtraction, even at the red wavelengths we need to go to measure redshifts at these high redshifts. But in addition to the spectroscopy, which was part of the Gemini large and long program, we also need deep imaging to measure stellar masses, to classify galaxies as star-forming or not star-forming, many other things. And so there was an additional effort by many members of our team through PI-led programs to obtain very deep imaging ranging from Mu through the IRAC bands from Spitzer to depths that are approaching that of the Cosmos and UltraVista survey. So some of our sample is actually taken from Cosmos and also from the Subaru XMM Deep Field, for which deep imaging exists. And what we wanted was to get for the rest of the clusters equivalently deep imaging from almost all 8-meter class telescopes on the ground. Ultimately, 40 proposals submitted over 4 years to obtain this coverage. We also have HST F160W imaging for all systems. So ultimately what we get for each one of these clusters, we have spectroscopy for many galaxies in the cluster. We can identify members and non-members. For each of these things for the spectrum, we have wide range of photometry and spectroscopy over the rest frame optical region for which we can identify individual spectral features. As a way to look at the overall sample, for Go Green and G-Class together, we have almost 3,000 redshifts, high quality redshifts. The plot on the left shows each one-dimensional spectrum stacked in order of increasing redshift. So you can see features like the O2 emission line moving redward as we move towards higher redshifts. Just a nice way to look at the data. And for those of you familiar with optical spectroscopy, above about 8,500 angstroms, the night sky emission gets really nasty, really hard to do good spectroscopy from the ground in the red. And what you can sort of see here is how clean things look even up beyond 1 micron. This is partly due to the nod and shuffle spectroscopy on Gemini and the excellent Hamamatsu red sensitive detectors that we use to obtain these spectra. This is how they're distributed in the plane of rest frame U minus V versus V minus J color, a popular way to separate star-forming galaxies in this bluer extended sequence from quiescent galaxies at the upper left. And we see right away that cluster members are predominantly quiescent, even at these redshifts, same as we see at low redshifts. The spectra are generally low signal to noise. Okay, they're sufficient to get a redshift, but the sample is large, and so you can stack populations of galaxies to get high signal to noise spectra that cover key spectral features that are useful for age diagnostics and other things. And that's my alarm telling me I need to stop soon. And so Christy is going to talk about this a little bit later, about how we can use these spectra to obtain physical information about the galaxies. So I'm not going to have time to talk very much about the first results, and that's okay, because there's talks coming up to discuss all of these things in more detail. We have 3 published papers and 1 that's just been submitted that are going to be discussed in the upcoming talks. We also have a number of papers in advanced stages of preparation that will also be discussed later this afternoon here and in the first half of tomorrow's public talk. I'll just highlight the one takeaway point is that the fraction of dead or quenched galaxies in these clusters is high. By some measures, it's higher than it is at low redshift. But through a number of things that we observe, including the shape of the stellar mass functions and the ages of these galaxies and their star formation rates, they don't look very different from what's in the field. And this is quite different from what we see at low redshift, and it suggests that this very high quenched population in clusters has a different origin from what we see at low redshift. So I'm sorry, I'm not able to review those results as I'd planned. I've run out of time, but you'll hear more about those later. This is the takeaway point, I think, is that we compare clusters at redshift 1.3 to clusters at redshift 0. Both are dominated by a substantial population of dead galaxies, but the origin of those that populate the higher redshift clusters seems to be quite different from those at lower redshift. Okay, you can find more information on our website, of course, in particular, information about the data release and how to obtain it. And you can find 2 papers on the publication page describing the survey description and the data release itself. This data release paper has just been submitted, but it is available on this webpage. So here again is just the agenda for the rest of the day. There are following Adam's talk on G-class, we'll have a number of science presentations. And again, I'll come back to talk to you at 1:10 p.m. Eastern time to introduce you to the data release contents and how to access that. And I will stop there so we can transfer to Adam to talk about G-class. And again, we're going to, I think, not have much time for questions immediately following talks, where I'm right at 10:20 here. Please put questions into the chat. So Adam, now over to you to talk about G-class.
Thank you, Michael. Screen sharing working okay? Yeah?
Yes.
Awesome. Okay, so thank you, Michael, for all the introduction and motivation for why we did this. When we were going to have this little meeting and release all the data, I realized it would be fun to kind of give a talk on G-class because it's something that, it's a survey we did a while ago that's kind of wound down, but it is sort of a precursor to Go Green. And I guess for me, it's kind of a fond, maybe farewell for G-class to have a nice little retrospective of what we did. And I think new people may wonder, you know, what is this G-class thing and how does it fit with Go Green? And so that's what I'd like to kind of put in perspective for you today. So G-class was a big group that worked on this cluster study. You can see everyone down below. The people I wanted to just quickly highlight were Gillian Wilson, who was the PI of G-class, and also Howard Yee, who was really instrumental in getting the survey going and giving us a lot of guidance as we did it. And then I just want to highlight two of my former students, Remco Vandenberg and Jasleen Matheru, both of who worked on G-class data in their PhDs and really produced a lot of the data products that are being released in this release and that you'll see a lot of the science in this talk. So just quickly, what was G-class? This was a spectroscopic survey of 10 rich clusters at about a redshift 1. Michael has sort of shown this. One of the things that was really fantastic for doing G-class is that there are 2 Gemini telescopes, not 1. In fact, you know, the GMOS instrument that we used is really nearly a clone between Gemini North and Gemini South. And that gives you an incredible amount of freedom when selecting targets and planning observations. And I think, you know, it's only with Gemini that we could really do a project like this. And so what G-class had is we had a pretty high spectroscopic completeness. We looked at these 10 clusters and we got about 500 cluster members across those 10 clusters. This was a while ago, and so this was quite a step forward, I think, for cluster surveys at the time. A lot of the work going back 10 years was sort of 1 or 2 clusters at a time with handfuls of redshifts. And here we really concentrated a lot of time in sort of getting homogeneous data across a reasonably large sample of clusters that allowed us to look at, you know, more subtle effects that are hard to do when you do 1 cluster at a time. So G-class was pretty big. It was about 222 hours. And this took place from 2009 to 2012 was the end of observations. Remembering that Go Green was the very first of the Gemini large programs back in 2014, we really did this before there were large programs, and we sort of just plodded ahead, continually writing telescope proposals semester after semester to sort of build up the data set over these few years. And so we were very lucky and very fortunate that both the US and Canadian techs supported us through those 3 years. But we ended data collection, I guess, about 8 years ago now, which feels like a long time. So what did we look at with G-class? I think Michael's kind of already shown this, but just to very, very quickly remind you, there were 10 clusters. They're sort of between redshift 0.85 and 1.3. There's about 50 members a cluster, you can see on the far right there. And another thing we did with G-class, which I think allowed us to do all sorts of exciting science, was that we got a lot of photometry for all these clusters. We had 12-band imaging pretty homogeneously across all 10, so you could do things like stellar masses accurately, etc. And so just to remind you of this, so when we designed Go Green, these top 5 highest redshift clusters in G-class became part of Go Green. In fact, these are some of the lowest redshift clusters now in Go Green. And in every way, the Go Green data that is being released now kind of vastly exceeds what we have for G-class in terms of photometry, and also spectroscopy. And so that's kind of how these two surveys meld together. The lower Redshift 5 clusters, that data is also being released as part of this data release. And of course, you know, the data is not quite as good as what you get with Go Green, but they're a little bit lower Redshift. And so hopefully, you know, those 5 clusters may also be useful to you if you're downloading the data release, et cetera. But that's kind of how these two surveys fit together. So I wanted to kind of do a retrospective, but I don't have quite enough time. So I guess this is the brag slide, but it's, you know, not really meant to be that way. Just wanted to point out that we published 14 papers already with GClass, and that we still have one more in prep. That's work that Jasleen Matheru is doing, and I'll show maybe a quick slide on that on the end. I have a 15-minute talk, and I have 15 papers listed here, so I obviously don't have time to talk about them all. But if you're interested, you know, the talk will be available, and you can read some of these. What I want to do for this talk is just kind of highlight some of the results from GClass that I think were the most impactful things we did. And I think you'll see a lot of the stuff that we just, you know, started to see interesting effects. We've come back with Go Green and done vastly superior analysis. So this is kind of the way this talk will be laid out, is just kind of give you a taster of the stuff we did, and then you'll see even better work from Go Green in the talks that follow mine. So what were some key results from GClass? I think the first thing that we found that, well, maybe it wasn't the first thing we found, but it's the order I'm going to go in, is that at high redshift, clusters are really compact and dense, and it seems like they grow in their stellar mass in an inside-out way. Okay, so what do I mean by this? Well, this is work by both Remco van den Bergh and Andrea Biviano, and there's a lot going on here, but if you look at the left-hand panel, this is the total mass of the clusters, and this is the total mass of the clusters, and it's the NFW concentration that you get for the total mass, okay, as a function of redshift. So the GClass is sort of the square here in the upper right. These are a bunch of different redshifts, and when you look at clusters and you look at their total mass profile, what you find is that, you know, it's pretty flat as a function of redshift, right? As clusters grow in dark matter mass, maybe it builds up a little bit, the concentration of these clusters, but not very much. And all those lines that you see are numerical simulations, predictions of how cluster concentration will change over cosmic time. Now, one of the things we were really surprised with when we looked at GClass was if you take the actual baryon mass in the form of stars, that is extremely concentrated at high redshift and really decreases as a function of time, all right? And this result is something we're still checking. You can see that really up in the upper right there, the GClass data has a very high concentration in its stellar mass, close to 7. But we checked that many times, and here's just a couple images on the right-hand side of some of the GClass clusters. These are color composites with IRAC being the red, and IRAC is a pretty good indicator of stellar mass. And you can see that these clusters are indeed, you know, very compact. There's a ton of mass down in the center, and then the amount that you see really falls off. And so this is kind of telling us that, well, the total mass of the clusters, you know, the mass profile of the cluster isn't changing much. The stellar mass profile is really changing, and clusters are growing in this inside-out way, which is, you know, not necessarily easy to explain, and probably something we should think about when we're looking at cluster galaxy evolution. Okay. So what else did we find? I think most of the work on GClass was concentrated on quenching and environment, and Michael alluded to some of this already, so I can be quick. But basically, you know, if you had to summarize everything that we found in just a couple sentences, what we found is that environment really strongly alters the quenched fraction of galaxies, but the galaxy scaling relations themselves don't really depend on environment at redshift 1. And so what do I mean by that? Well, this is work that Remco did during his PhD thesis, and you'll see a much updated version from Go Green shortly, but this is the stellar mass function of galaxies. You see clusters on the left, the field on the right. Star-forming galaxies are in blue, quiescent galaxies are in red. And again, Michael already alluded to this, but we really clearly saw a significant excess population of quenched galaxies in clusters at redshift 1. And at the time we were doing this work, it's now, it's been 7 years, 8 years, that was still debated. There were papers that claimed a reversal of the star formation density relation, that clusters are actually more actively star forming than the field. And I think, with the high quality G-class data, at least for this cluster sample, we showed that that's not really the case, right? That there's still a high abundance of quenched galaxies in clusters. And in fact, even if you look at the field, right, the field is still dominated by quenched galaxies above masses of about 10.7 as well. Now, there's a lot you can get out of this more than just saying an elevated quenched fraction. There's all sorts of interesting things about quenching, and you'll see the Go Green results in Remco's talk right after mine, and I think all sorts of interesting things to discuss about what this means, particularly the shape of these mass functions. Now, there's an elevated quenched fraction, but now you start looking at galaxy scaling relations, and you start to find out that things actually don't really depend very much on environment. So this is a paper I wrote, which feels like a long time ago, and I'll show you a few plots from it. They all kind of look the same. This is the specific star formation rate of star-forming galaxies as a function of cluster-centric radius along the bottom, and then there's a field out here on the right, and the different curves are different masses. So high mass galaxies on the bottom, low mass galaxies are on the top. And what you see is that, of course, at any fixed environment, there's a very different specific star formation rate for each mass. So lower mass galaxies have higher specific star formation rates. But to 0th order, these curves are flat, okay? Which means that the specific star formation rate of star-forming galaxies depends on mass, but it doesn't really depend on environment. And we've done the same analysis with Go Green. This is great work by Lindsay Old, and you'll see her talk coming up soon. Sort of largely reproduces this, but with some subtleties that make interesting implications about quenching, and I'll let Lindsay tell you about that result from Go Green. We looked at other indicators of other scaling relations. Sorry, one of the classic things to look at is the D4000 of galaxies. This is the strength of the 4,000 angstrom break. You've got quiescent galaxies on the top, star-forming galaxies on the bottom. The different masses are the different colors, and it's as a function of cluster-centric radius out to the field on the right-hand side. And what you see again is if you pick, a fixed environment, D4000 correlates with mass. Massive galaxies have stronger breaks and are therefore older. But to 0th order, all of these curves are pretty independent of environment. There's maybe some slight trends, but in general, the D4000 scaling relation is independent of environment. Christy Webb has done fantastic analysis of this on Go Green, much more sophisticated than simply measuring D4000, and indeed sees similar things and has all sorts of interesting implications of those. And so I'll let you look at her talk. One of the other scaling relations we looked at is the so-called size-mass relation. This is work from Jasleen Matheru's PhD thesis. This is the size, effective radius of galaxies as a function of mass. You've got the clusters on the left. You've got field galaxies on the right from 3D HST. And there are quiescent galaxies are in red, star-forming galaxies are in blue. And the black lines are the best fit scaling relations from 3D HST. And what you can see is if you map those onto the clusters, they're almost the same. Now, Jasleen found that that cluster galaxies are about 25% smaller than field galaxies, but it's a rather small effect. Again, suggesting that environment doesn't have a strong effect on galaxy scaling relations. And of course, as is the theme of my talk, we're also looking at this in Go Green, and this is great work by Jeffrey Chan using much deeper HST data, and I think he'll show you what he's finding there. Again, I think largely consistent with this. Okay, so I have 6 minutes, which is pretty good. So I think the other really key result we found in G-class was looking at post-starburst galaxies. And what we found is that post-starburst galaxies are very common in clusters at redshift 1. And I think if we really want to understand the quenching that goes on in high redshift clusters, we probably should be putting a lot of effort into studying post-starburst galaxies. So just in terms of abundance, this is again from this paper I wrote a while ago. Post-starburst galaxies are clearly more abundant in high redshift clusters than they are in the field. The field's here on the right. Post-starburst galaxies are only a few percent of field galaxies, but they can be up to 5 to 10% of cluster galaxies, depending on mass. Particularly, there's a lot of low mass post-starburst galaxies in the G-class clusters. Again, we are looking at this with Go Green in more detail. This is work by Karen McNabb, and I think you'll see her talk a little bit later on. I'm interested to see it myself. I think a lot of the stuff we've seen with Go Green is, similar to G-class, and obviously much better data and much more interesting implications with the better data. But the post-starburst thing may be different between the Go Green results in G-class, and so I'm curious to see where that is at when the time comes. I want to make the argument that these post-starburst galaxies really are a key transition population. This is the phase space diagram of the G-class clusters. So this is on the y-axis, this is line of sight velocity, how fast the galaxies are moving basically as a function of radius. People have done this for clusters for a long time. G-class doesn't look very different than low redshift clusters. You can see at sort of small radii and low velocities, there's a lot of the quiescent galaxies, which is what you expect from something that's been a gravitational potential well for a long time. Star-forming galaxies are kind of everywhere. This is what you expect from an infalling population. And when we plotted this for post-starburst galaxies, it's rather conspicuous because you can see there's a lot of them sort of at intermediate radius between the two. And in particular, there's quite a few of them that are moving at high velocities. And so if you think about quenching, post-starburst galaxies have just recently quenched, and lo and behold, you find them pretty close to the cluster center moving at high velocities. That's interesting implications for what the quenching might be. And I'm running out of time, so I'm going to go quickly. This is all, of course, published, and you may have even seen it before. We did some work, and Sean McGee did fabulous work going into simulations and trying to plug in places where galaxies might quench and how long of a timescale it might be in order to reproduce this phase space diagram for post-starburst galaxies. And so on the left is the real measurements from G-class, and on the right is where recently quenched galaxies should be from Sean's simulation work. And this was the best match we could find, and you can see it's pretty close. It's sort of these simulated post-starburst galaxies are approximately the phase space of the observed ones. And the way to get those is having quenching beginning to occur at about half the virial radius on a very rapid time scale, okay? And so if you really believe this analysis, it means we're actually maybe even identifying at what radius cluster galaxies start to quench and how long that quenching process is, at least for this post-starburst population. One interesting thing about the post-starbursts is that they really are, from a scaling relation standpoint, intermediate between star-forming and quiescent galaxies. This is a recent paper by Jasleen Matheru. This is the mass-size relation, again, star-forming galaxies in blue, quiescent galaxies in red. And when she plotted the post-starbursts, I thought it's almost too good to be true. You can see that in the mass-size relation, they really lie intermediate between star-forming and quiescent galaxies. And if you look in the upper left panel here, this is Sirsic index, and you can see the post-starburst galaxies also have Sirsic indices that are intermediate between star-forming and quiescent galaxies. And through much modeling, what Jasleen found is the only way that you can really get this is if you not only just have the disks of star-forming galaxies fade, you really require them to fade from the outside in. It's the only way to get this compactification so severe, which is really interesting implications about quenching. What do I got left? 1 minute. Okay. I will say one thing very quickly, which is that the one thing we have in progress is that Jasleen is working on looking at the H-alpha sizes of galaxies in these clusters from our HST GRISM program. Won't say much about that. I will skip how GRISM works, and I will just get to the results very quickly. What you see on the left here is these are results from Nelson et al. From 3D HST, and it is the H alpha size of galaxies in blue and the continuum size in black. And you see that at redshift 1, the H alpha sizes of galaxies are bigger than their continuum size. But our preliminary result from G-CLASS on the right is that the inverse is true, particularly at low masses. Galaxies have smaller H alpha sizes than continuum sizes. And to me, this is real evidence that ram pressure stripping might be happening in low mass galaxies at high redshift, which I think is a really cool thing. And look forward to seeing this in the coming months when she submits the paper. So just throw up my conclusions there. It's fun to tell you about all the things we did with G-CLASS, and I look forward to seeing all the updates on this from Go Green.
Thanks, Adam. That's great.